In this video, I'm going to show you further problems on Gauss law. Particularly, I'm going to demonstrate to you how to use dot products in calculations. Our learning outcome is going to be to perform dot products, or what is also called a scalar multiplication, and then apply Gauss law to solve problem. Let's have this question quickly. So we have a box here. It's one of its corner is placed at position 460, and it is in a volume. Then there is a charge placed in it. We are supposed to determine that charge, given that there is an electric field being produced around this box. What is interesting about this electric field is that it is non-uniform, and it varies according to the y direction. It varies in the y direction. Any direction it is uniform, but along the y-axis it varies. So maybe at this point it is high, at that point it is slow, and that kind of thing. So along the y direction, the field is varying. So we are supposed to determine the total charge enclosed in the cube. We are going to use Gauss law, and let's state it again. It is the electric flux, across a closed surface area, and that one must be equal to the total charge enclosed in that surface area divided by the permittivity of free space. So what it means is that we need to divide the whole surface area into smaller surface areas, and then take the dot product with the electric field. So we have the surface to be divided into smaller surface area, and this is a box. It is more convenient dividing it into 6 different flat surface areas, and the areas I've labeled it as a plus x. That means the area vector which is protruding out of this surface facing you is a plus x. That is, it is in the x direction. The area vector, it is in the x direction. Then we have that of a plus z, which is in the z direction. That's the area vector for this surface. It is pointing in the z direction. Then we have that for the a plus y, which is pointing in the y direction. Remember, area by itself is a scalar quantity. By multiplying by the unit vector makes the whole value a vector quantity. Now, this image is showing you just 3 surfaces, and each of them has an opposite surface. This y surface has an opposite surface that is pointing in the negative y direction, and then we also have the this surface pointing in the x direction, having its counterpart, the opposite one, pointing in the negative x direction. So what is the first area, which is the a plus x? We just multiply the size, find the magnitude, which is given by, we have the surface area, the size of the box to be 4 meters, 2 meters, and then 3 meters. So 4 meters will be the longest one, the length. We have the breadth to be 2 meters, which is the side. To be, we have the height, which is 3 meters, which is 3 meters here. So if you want to find the surface area, it is this side multiplied by that side. So it is 4 multiplied by 3, giving us 12. And we are multiplying it by the unit vector in the direction of x. That will be I. Okay. We can do same for the y direction, which is 2 multiplied by 3, giving us 6. And the unit vector is in the direction of what? J. The same thing we can do for a plus z and get this is 4 multiplied by 2. This is 4 multiplied by 2 here, giving us 8k. We can go on and find the surface areas for the hidden ones, the surfaces that are hidden. Okay, so now we have all the 6 surfaces for the box. Let's see if we can calculate the flux. We can calculate the flux for all the surfaces. The flux for the first surface will be the electric field dot multiplied by the surface in the positive x direction, and we are going to get 18. But let me go through this one and show you very, very important point about dot product. We have the field which is given in this direction, which is given here, dot multiplied by 12i. What we need to do is to expand with our usual algebraic expansion. Dot 12i multiplied by 1.50i. This is it. And we get 18 for it. Because we have I dot I, this one will give us a value. It will give us non-zero value, which is 18. Then for the second one, we have 12i dot negative 3.2 y squared j. We don't need to worry about this one because it is going to be I dot j, and that is going to give us 0. Similarly, we have 12i dot k, something k. And so long as we have unlike unit vector terms, the dot product is going to be 0. Unlike unit vector terms, so we have I here, dot multiplying j here, it will make the whole dot product 0. We have I here, multiplying k here. Since the unit vectors are not the same, dot multiplying them will be 0. Remember, in the cross product, that wouldn't have been 0. Remember. Okay. So for this dot product alone, we are going to get 18. Let's move on to the second one. We do the same thing, but this time around, there's very important. There's one important thing about it. Because the j dot j is not going to be 0, we need to also evaluate y squared here. So we are doing this one for a plus y. We need to find the surface where it is placed, and it is placed at y equals 6. So if it is along the y equals 6, then we are going to change this one to 6 squared and evaluate it. If we do this evaluation, we are going to get negative 3.2 times 6 squared multiplied by 6 here, and that is it. And because j is multiplying j, which will be 1, we have the value to be negative 691.2. All the other dot products are 0 because they don't have like unit vector terms. K dot j is 0. J dot I is also 0. We only have j dot j, which will give us this value. So our next term is going to be negative 691.2, which will place it here. We can go on to do for this one, and it's as we already know, and keep on doing for the other 3 surfaces, and we have these terms for ourselves. Some few ones will cross out, negative 18 and negative 18, plus 18 and negative 18 will take care of themselves. That means they will cancel out, and minus 40 plus 40 will also cancel out, leaving negative 691.2 added to 76.8, and eventually giving us 614.4 Newton meter squared per coulomb. That will be the surface integral that we've calculated for this box. And from Gauss law, this surface integral that we've calculated should be equal to the expression here. So let's see how that one also goes. So we put negative 614.4 here and equate it to the Q enclosed divided by the epsilon naught, which is 8.85 by 10 to the power negative 12. And the whole thing comes out to be minus 5.4 by 10 to the power negative 9 coulomb. In other words, negative 5.4 nanocoulomb. That will be the charge enclosed. A very important point is that this may not necessarily be a single charge. It may be that there are several charges, but the algebraic sum of those charges should add up to should give us something like, the algebraic sum should give us minus 5.4 nanocoulomb. So that's it for now. I think this one will help you to complete your assignment. Thank you.